Good morning, or good afternoon, or good evening, whenever you are. This is going to be the first Stat 50 lecture, and I'm going to start off. Um, so let's get started. I hope you first of all watched the previous video. It has a lot of good basic concepts that you should know for understanding continuous random variables. But the problem is it doesn't go quite deep enough. We are going to be using calculus level stuff. We're going to mostly just use calculus for our notation and for some of our concepts, but we're not going to actually be doing a lot of calculus. In fact, I'll show you shortcuts to use technology to do the calculus steps. Okay, so let's do a quick review of what you should have seen on the previous video. One small difference from that video is they refer to the density curve, and the density curve basically is the curve described by the function, or the continuous density function, CDF, which for short we will just be using little f of x. Same little f of x from calculus, and when you graph little f of x, you get your density function. So one property that they went over about density functions or density curves is that the area under the curve always has to equal 1. And by area under the curve, we mean area under the curve and between two bounds and between the x-axis. So, for example, we just have a basic curve, and if these were two values A and B for x, two values that x takes on, then the area under the curve is the area of this part here. And let's look in terms of calculus. So we have a way to describe this in calculus, the same situation, and that is to use this integral notation. So integral a to b, that's how this is read here. And if we're going to calculate the area under the curve, we write that curve's function. And then we write this little dx. Now, the dx is something, if you've taken second semester calculus, you should be very familiar with. But if you haven't, we'll just ignore it. It's an important detail, but for our purposes, we won't be getting into the nitty-gritty of calculus. Okay, but what you do need to know is that this is expression for the area under the curve f of x between a and b. With this notation now, we can use this to actually calculate probabilities or compute probabilities. So one counterintuitive thing about CDFs is that if we write this notation p of x equals some value, in this case it's not equal to f of a. Now your instincts might tell you, might want to do this because back when we were using discrete functions, this was true. This little p of a, this discrete probability function actually does, or probability mass function instead of density function, does work like that. However, when we're using these continuous ones, the probability of p actually equaling a is always equal to 0. And so because any exact value is going to have 0 probability. So the only way we get non-zero probabilities is that we look at the probabilities of x falling in some range. So for example, the probability that x is between a and a second value b is going to equal the area under that curve, or as we write it in calculus notation, looks like that. Okay, so this is the probability that the value of your random variable is between these a and b is going to be equal to this expression here. And note, because the end values a and b are both equal to 0, this is also equivalent to this expression. So whether you write A including B, or whether you include A and B or not is irrelevant. You still get the same probabilities because you still end up with this function right here, this calculus function. And that's how you calculate the probability of a random variable being between A and B. Okay, let's, so whenever we are doing any random variable, we're always interested in these basic things, the mean, variance, and standard deviation. For the mean, we're going to have this formula here. So the mean of f of x is going to be the integral from negative infinity to infinity, meaning just all the values that x could possibly take on. And we're going to do x times f of x dx. Okay, note, this is very similar to the discrete version. So let's quickly look at the discrete version. The discrete version for the mean was this. So we can see the only difference here, well, what's been changed is that the integral, or the summation, has become an integral, and the probability mass function has now a probability density function. And other than that, it's the same pattern. Okay, so let's look at the variance. So if we get sigma squared x, or the variance, very similar to the mean and to the discrete version. We're just going to take, instead of x, we're going to take x squared. And this part is all the same. And then, similar to the discrete case, we're going to just subtract the mean squared. Okay? Again, totally analogous to the discrete case. Let's quickly write that down because it's familiar. And okay. And then lastly, standard deviation. This will be easy. We just take that, and of course variance is written as standard deviation squared, so we just take its square root, and there we go. We've got all the basic measures of central tendency.